All right, welcome to this video on translations in geometry. It's one of the transformations that we're going to be doing in our unit on congruence transformations. So let's start with the informal definition of a translation. It's a transformation that slides all points on a figure the same distance in the same direction. We do this using a vector. A vector has one quality in common with a ray. We know a ray has an endpoint and then goes infinitely in one direction. A vector has an endpoint and goes a specific distance in one direction. So a ray, like ray, let's call it AB here, starts at point A, goes in the direction of B infinitely. But a vector, AB, we note it with only the top part of the arrow on the ray, starts at point A and ends at point B. And the longer the vector, like the more strength there is in the force. Vectors are used a lot in physics to represent, mass. So you could have a mass of a book pointing down versus the mass of a paperclip. And so since the vector for the book is longer, that means it has a higher mass or a higher weight than, say, a paperclip. So vectors have two quantities, magnitude and direction. So in this case, for the book and the paperclip, we have a vector going down for the book because that's the direction of its mass based on, the gravity of the earth, and the paperclip going down. But the paperclip is shorter because the paperclip weighs less. So you use those in physics in that way. We're not going to quite use them that way here because this is just an introduction to vectors. But I do expect you to know the difference between a ray and a vector. They both have direction. That's what they have in common. But a vector has finite length because it stops, as opposed to a ray that has infinite length. A vector also has what we call an initial point and a terminal point. So the initial point is where it starts, and of course the terminal point is where it ends. Sometimes they're called tips and tails, but more recently, initial and terminal are easier to remember. Tip and tail, I always get them backwards myself on which one is which. So we will go with the terminology initial point and terminal point. So a vector has finite length called the magnitude. You need to know the initial point and the terminal point. All right, so you can write a vector in two ways. You can write it in coordinate form, where you write what you do with the x and what you do with the y. So like x plus or minus a number, y plus or minus a number. Or you can just write the numbers, and that's called component form. And we're going to do that for this little situation over here with the one star mapping to the other star. So we're going to write that both ways. If you look at this distance, it's going across 8 and then up 4. So we could say the vector for all the x's from the pre-image to the image, because this has the prime, all the x's add 8 and all the y's add 4. Or in component form, we would write positive 8, showing that they all move right 8, positive 4, showing they all move up 4. If you are asked to find the distance or the length that the object moved, I'm going to add this little side topic here for you. That means I want to know what this distance is. Like a lot of students will accidentally do 8 plus 4 and say it moved 12 because you went right 8 and up 4, and I totally get that. But if I want the total distance as if it slid directly there, then I would use Pythagorean theorem. And I would work that out. So 64 plus 16 is 80. That equals d squared. So we would square root both sides and get that square root of 80 is d, which is 4 root 5 when you simplify the radical, or approximately, it's just a little less than 9, because 9 squared is 81. So it looks like it rounds to 8.9. I was wondering if it would be enough to round to 9.0, but it's not. Another thing I want you to understand about vectors is that not only is this a vector moving that point A to that point A prime, all the vectors moving any pre-image point to its image point, if we draw them all, you will see all of them are the exact same length and in the exact same direction. They're all parallel to each other. So the formal definition of a translation is it maps all points M to M prime or A to A prime or whatever, such that M prime is the vector V, the distance of the vector, the magnitude. Yes, absolutely. So all of these are the vectors and they are all the magnitude of square root of 80 or 4 root 5. And M prime is parallel to the vector. All of these are parallel to each other and to the original vector of movement. Our notation that we're using of what you're doing, how you're doing it, and what you're doing it to, and where it ends up. Translation, you don't have to capitalize all three of them. You have to have a vector, just like with a reflection, your subscript has to be the line that you're reflecting over. Here, it has to be a vector, and it can be written in component form, coordinate form, or if you just have a picture of the vector, like let's say I just said this vector 8, 4, and I drew this vector on your paper, then, and I just called it like vector V. Okay, you could name the vector and then you would go and count it yourself. So let's do an example like what might be coming up on your practices and assessments. So we are given triangle HIJ with certain coordinates, -5, 4, -2, 5, and -3, 2. We're going to graph that pre-image. That's H. Okay. J. And just to make it nice and neat, I'll use my segment tool here. Okay, that's our pre-image vector. And we are going to translate this by, I've given it to you in component form, 7, -5. So you can write it that way here, or you can write x plus 7, y minus 5. Any way you want to write it there is fine. So we need to find the image of it. In our initial lesson on rigid motions, we did do some of these. We just didn't call them translations at the time. So all the x's, I'm going to add 7. I'm going to do those first. So -5 plus 7, -2 plus 7, -3 plus 7. And then all the y's, I'm going to subtract 5. 4 minus 5, 5 minus 5, 2 minus 5. All right, now let's graph the image and we will see what happened. 2, -1 is h prime. 5, 0. I prime, I was getting ready to make that a j. And 4, -3. I didn't use my line tool, but this is not terrible. Okay, so we can see every point in there moved right 7 and down 5. Right 7, down 5. Right 7, down 5. So we could draw all the vectors, but I'm not going to because I don't want to make it look bad. But that vector you can draw anywhere. Right 7, down 5. So this would be the vector that all of them moved by. All vectors that are the same length and going the same direction are congruent to each other. So that would be our vector for this one. All right, let's talk about sketching a translation. So we're going to translate this triangle by this vector. So what I'm going to do is I'm going to copy that vector, make it about the same length, and going in the same direction, which you can use a ruler or whatever. So that looks like it's about that. I should have made those lines dotted, but I'll do that if on the next one. So the terminal, this would be C prime, B prime, A prime. You want to try to make them look parallel to each other. Oops, that's not what I wanted. And now I draw my triangle. It almost looks like a three-dimensional image when I get done, but you can see it's really easy to sketch a little vector translation. Okay, next we're going to talk about constructing with a compass and straight edge if we were asked to construct it. If you're asked to construct it, what you're going to need to do, because all the vectors have to run parallel to each other, that means we're going to have to first construct parallel lines. Now, I don't like to do it all three times. I mean, we would have to construct a parallel line here, here, and here. And if you remember, when you construct a line parallel to a given line through a given point, the first thing you do is you make a transversal. Then you copy the corresponding angle to get your parallel line. To do that three times, because you have to do it for each vertex, would be kind of crazy. So what I will allow you to do in class, if you have to do one, is you will construct one parallel line, and then you will trace the triangle with your patty paper that we have in class, and you will just slide it along there to its new location. And you'll trace this on the patty paper as well so that you don't angle it as you slide it. So we're going to do that construction one time for whichever point on the figure is most convenient for drawing purposes. And I think that's point B here. So I'm going to use point B, and I'm going to first make a transversal. I think I could have done that better. Let's do it better. There we go. That's going to be my transversal. Doesn't matter what angle, as long as you connect B to this line. I'm using D, the initial point, but you don't have to. I could have used another point on here to make my parallel. All right, now I'm going to copy, like I'm using a compass here to make my arc marks. Okay, oops, that's not good. Okay, I'm using D as the center of the circle now, B as the center, and I can see it's going to go through this point. So this is going to be my parallel. Then the question is, all right, now that I've got a parallel line that B is going to move on, my vector is going to be on here, I have to make it the same length. So we can use the idea of copying a segment. Okay, measure the vector and copy it onto the ray. So back to our original constructions, copying corresponding angles, copying segments. So I'm going to measure that length of that vector with D as the center and mark that off right here. Okay, so that would be like the point that B prime is going to move to. And then in class, what we'll do is we will take a piece of tracing paper. We will trace our triangle. We will trace our vector. Okay, and we will move B to here so that the entire triangle is on top of where its new location would be. And then you can just tape it down. That's fine with me if you do that, rather than having to do the construction three times. And then there would be your new triangle. A prime, B prime, C prime, right here. All right, let's talk about a glide reflection. A composition of transformations, including a translation and a reflection. Okay, glide is in slide. And then, of course, reflection is called a glide reflection, but it only is a glide reflection if the reflection line is parallel to the translation vector. So if we look here, we have a line of reflection here that this triangle is flipped over or reflected over. And then afterwards, we take that triangle and we slide it up this vector to a new location. Because the translation vector is parallel to the line of reflection, it is a glide reflection. And when that happens, you can reverse the order of the translation and it will end up in the same place. You could take this triangle and slide it up here and then reflect it over, and it would still end up in the same place. That is called a glide reflection. And you will have to at times perform glide reflections, like right here. We'll go back and hit this second thing in a minute. Perform the following glide reflection on A, B, C, D, and we have points. I'll graph the pre-image. A is -1, 1. B is -3, 4. 4, 1 for C. And D is 2, 4. Going to graph that image, or pre-image rather. I meant for that to be a solid line. Okay, and we are first going to translate at 0, -8. Now, I'm not going to make a chart for this because I don't think we need to slide it down 8 and do the arithmetic. So we're just going to slide it down 8 spaces. I'm going to make this one light because it's not going to be our final location, but we do follow the order of operations and do inside the parentheses first. Okay, so there is our first item that gets done. So that would be like your A prime, B prime. Oh no, that's D prime, sorry. C prime, A prime, and B prime. All right, then next, afterwards, they want us to reflect it over the line x equals -3, which is, of course, a vertical line. So we'll graph that vertical line at -3. There's our line of reflection. I'll make it dotted. I like to make the final image solid and everything else dotted. Okay, so we're going to flip these points over that line right now and see where they end up. So B is on the line of reflection, so B double prime will also be on the line of reflection. D is 1, 2, 3, 4, 5 away, so we go 5 on the other side for D double prime. 2, 2 on the other side for A double prime. C is 1, 2, 3, 4, 5, 6, 7 away. So I'm going to go 7 on the other side. C double prime. And there is our final image of where this is going to be located. And we could write down the coordinates if they asked us to, but they didn't. So there's graphing a line, a glide reflection. And I just want to, highlight again the fact that this translation vector of down 8 is parallel to that line of reflection. That's why it's a glide reflection. You can do a composition where they aren't parallel, but it would not be called a glide reflection. Okay, let's talk about another property that you should be aware of, which is a composition of reflections in parallel lines. Now that we've learned reflections and now that we've learned, translations, this is going to connect the two. So let's do a composition of reflections in two parallel lines. So we are going to basically first reflect over line M, and then we're going to reflect it over line N afterwards. Remember, your subscript has to be your line of reflection. And we're going to do that to the, I guess I'll color it in green because it is a green triangle. The green triangle. Okay. Well, it's a green right triangle, so I guess I should be, for the sake of accuracy, make it a green right triangle. All right, and when we do that, we're going to see that some special property takes place. So first I'm going to reflect it over this line. So I'm going to maintain the distance on the other side. Like if I call this distance X, it has to be X over here. All right, I'm not going to color it in. All right, then I'm going to reflect it over line N, which means that distance has to be maintained. So let's say this distance is Y. I'm going to have the distance y over here as well. And this is just a rough sketch. Okay. Very rough sketch. Let me try that a little bit better. Okay. Slightly better, but not much better. All right. So the idea is to understand what happens. If you remember, when we discussed reflections, we talked about how it flips the orientation. So like if this triangle was ABC, this would be C prime, A prime, and B prime. So if I named the triangle clockwise, starting with A, B, C, and I start with A here and go clockwise, it's A, C, B. It flips it. It was pointing to the left, now it's pointing to the right. But then when I reflect it again, it reverses the orientation again, which means that the orientation is back to what it started with. Triangle ABC is still triangle ABC. All right. That's one of the things. So the orientation is flipped back. But the property that's new here that we want to understand is what happens when you go from the first figure directly to the third one. You can see that it looks like it's just been translated. If you don't look at this one, it looks like it's been translated directly over. So what is the translation vector, the magnitude and direction that is happening here? Well, a composition of reflections in two parallel lines is equivalent to we just said it looks like a translation of something, the distance between the lines, which is what it says right here. Okay, well, the distance between the two parallel lines, if we look at this picture, is an x and a y. So we'll call it x plus y. Now let's look at what looks like happened as far as the vector goes. So like if I'm going from C all the way to C double prime where it ends up, and that's my vector, you can see that that distance is the x plus the x plus the y plus the y. So that would be 2x plus 2y, which is the same as writing 2 times x plus y. So it's twice the distance that the distance between the two parallel lines is. I'll mark those lines parallel for you. So it's a translation of twice the distance between the lines in a direction of, okay, we need our magnitude and our direction. This direction is directly perpendicular to both of these lines. There'd be right angles there. So in a direction perpendicular to the two lines. You need to know that property. So like if I were to give you an assessment and I were to say, hey, the distance between the two parallel lines here is 7. How much would the translation be? You would say 14. Oops. All right. Our last example has to do with when you do two translations to an image, what's the kind of overall shortcut that you could take? So figure A is translated by -4, 5 to reach A prime. So we can start anywhere. I'll just put A as a point at the origin. So it goes -4, 5, which means it goes left 4, up 5. All right, so that's where A prime is when we do that. And then it goes by the vector 7, -1. So from here, it goes right 7 and then down 1. So that's A double prime. What single transformation would map A to A double prime? Well, let's figure that out here by adding it up. We could go right 3 and up 4. So the single one would be 3, 4. So if we look at our two original vectors, we have -4, 5, and then we have 7, -1. What could we do with those two vectors to get 3, 4? Well, -4 plus 7 is 3. 5 minus 1 is 4. You can add them. So you can add any number of vectors to get a shortcut. So the sum of any two vectors a comma b and c comma d is a plus c, add the x's, b plus d, add the y's. So that's an introduction to vectors. It's not everything. We haven't added vectors with pictures, which we will do later when we get to our unit on trig, but it's enough to get us through what we need to know about for translations. So join us for our next video where we will be discussing rotations as we finish up this unit on congruence transformations.